Alrighty, so, this is mostly going to be about 3.9, but I did want to include one thing from 3.8 very quickly, and that's mainly that it gives us a couple more specific functions that we can take the derivative of to add to our library. So before this we had power functions, we had e to the x, and then we had trig functions, right? So the one thing from 3.8 that I want to highlight is the inverse trig functions. So I'm going to go ahead and just write them all out here. And they still behave in a nice sort of pattern because the cofunctions always have the inverse cofunctions always have the exact same derivative, except for the co-version has a negative in front of it. So I could really just write down half of these and have all 6 of them, technically. But I'll go ahead and write out all 6 of them. Largely because I'm going to skimp on some of these later on in this section, so I might as well give you all of them now. Alrighty. The annoying thing, at least for me, for memorizing them is that they all do have the same sort of x squared plus or minus 1 aspect to it. And so that can get a little bit annoying, but that's what we have for our inverse trig function derivatives from this section. Now from 3.9, which we're going to focus on a lot more, this is one where we learn more about our logarithmic and exponential. And it specifically, this section is sort of focused on something we call logarithmic differentiation. Right, so first off, we have that the derivative of the natural log of x is equal to 1 over x. And that's specifically, excuse me, the natural log of x, right? All of the other logs, you'll want to use the change of base formula to put it into natural log terms before you use this formula. Because this formula, the derivative of the natural log of x is equal to 1 over x, is specific to the natural log, not just logs in general. We also get one for the generic exponential. Right, and so that's if we're taking the derivative of any constant b to the x, then we get the natural log of b times b to the x. Right, so this still matches up with what we knew before. Before we knew the rule for b specifically equal to e, and if b is equal to e, then the natural log of b is 1. Right, so this doesn't contradict anything we've learned before. The other sort of rule that we have here is a combination of this logarithm rule and the chain rule, which is that if you are taking the derivative of the natural log of a function, then that equals the derivative of that function times 1 over that function. Right, so that's just applying the chain rule to this function right here. This part of it is the derivative of the outside with the inside plugged in, and this part of it is the derivative of the inside. this is the thing we're gonna focus on for most of this section. There is also included in this section the hyperbolic trigonometric derivatives, or the derivatives of the hyperbolic trigonometric functions, and the derivatives of the inverses of the hyperbolic trigonometric functions. Those are nice and cool and good things to have in our arsenal, but unless you specifically take this to somewhere where that sort of thing is specifically useful, it's not quite as generically useful as the rest of the stuff is. So I'm not going to spend half a page on my tablet rewriting that out. If it comes up, then there are tables in your book, right? And it's just a matter of another few lists of derivatives that we have, right? But what we really want to focus on is this logarithmic differentiation, right? So I'm going to throw a problem at us. There we go. All right. So, whoops. I want to write that all over again. So we're going to move this down here. I'm also going to be clever and copy it for reasons that will be clear later. And then I'll redo this part. There we go. So we want to find the derivative for this following function. Now, we can look at this here, and this is a function that we could absolutely figure it out without much problem. I mean, there'd be plenty of problems and wailings and gnashing of teeth and all of that stuff, right? Because we would have to use the product rule 4 times at least. We'd have to use the quotient rule, or we'd have to use the product rule even more times and use the chain rule a bunch of times. And even if we decide to use the quotient rule, we'll still have to use the chain rule for at least 4 of these times. So we could do this using the tricks that we have now, or we had before this section, and it would be utterly obnoxious, and it would take us an entire exam period just to do this one problem. Or we could be really clever and use logarithmic differentiation, right? So the idea behind logarithmic differentiation is that if I take the natural log of f of x, right, then we have rules for expanding logarithmic expressions. We have rules for that turn all of this product and quotients into sum and differences, right? And so if we do that, right, so using the logarithmic expansion rules, any products on the top become sums. So we get this guy. And any of the factors on the bottom become subtraction. I'm hoping to have enough room here. There we go. kind of enough room. I'll try to be more careful about that next time. Right? So that's sort of the first basic rule of logarithmic expansion. And then I can pull those powers out. So this was getting rid of the quotient and product rule necessity. Now I can get rid of the chain rule necessity by pulling those powers out front. Okay. That kind of fit better that time. Kind of. So we can pull those powers out front, and so now all of the things inside the natural log, we can find the derivative of pretty easily, right? That's just a collection of power functions, right? So if I find the derivative of this guy, right? That means going in one at a time and finding the derivative of each of these pieces. Right? So, that means saying 2. So the derivative of ln of something is the derivative of that something divided by that something. So the derivative of ln of 1 plus x squared is the derivative of 1 plus x squared all over 1 plus x squared. The derivative of 3x, ln of 3x plus 1 is the derivative of 3x plus 1 divided by 3x plus 1. The derivative of ln of 3x is the derivative of 3x divided by 3x. The derivative of ln of 2x squared plus 1 is the derivative of 2x squared over 2x squared plus 1 minus the derivative of the natural log of x to the 6 plus x to the 4th is the derivative of x to the 6 plus x to the 4th divided by x to the 6 plus x to the 4th. Right, so hooray and whoopee, right? It might seem like we've got the derivative of something that we didn't care about in the first place. But if we use that exact same rule that we've talked about, that we just used 1, 2, 3, 4, 5 times here, we know that this is the derivative of the function we care about divided by the function itself, right? So that means that f of x itself, or the derivative of f of x, we can multiply both sides by f of x, and we get there it went. The function itself, gonna make that smaller, we're gonna need a lot of space here. Times all of this junk. Whoops. I know the problem. That's what I need to do. Haha. There we go. really hard to read, but y'all know where I'm copying and pasting from, so hopefully that won't be too bad. Let's do that and go back to here. Right. So that looks horrible, and good Lord, I don't want to simplify that, and I don't really want to look at what y'all come up with and you simplify it, but we can just leave it at that, right? We have found f prime of x. It is f of x itself times, the derivative of the natural log of f, right? So using logarithmic differentiation uses this rule that we came up with up here, the chain rule using logarithms as the outside function, in two different ways. One, to find the derivative of all these individual pieces, and two, to get the derivative of the thing that we want out of the derivative of the thing that was easy to find, right? Because the idea here is that finding f prime of x just from this alone is really, really difficult, or at least really time-consuming. But finding the derivative of the natural log of that is pretty easy, for all that it takes up way too much space, especially in my handwriting. Right? So we use the easy thing in order to get the hard thing, because we have a formula that relates them. Right? So let's do another one. Let's do there we go. That's better. Yeah, we'll leave it at that. This one probably wouldn't be too bad to do either way, right? We could do this either using the quotient rule and the product rule, or using the product rule twice and the chain rule an extra time. But we're going to do it logarithmically just for the practice, right? So we're going to find ln of the function. All right, so ln of cosine of x square root of 1 plus x all over 5x plus 1 to the 6th. Right, we're going to expand that logarithmic expression. So all of the factors up top get a plus sign. All of the factors down below get a negative sign. Right, then we're going to pull off any powers. Cosine of x doesn't have a power. This root has that secret 1/2 power. And this guy has the very overt 6th power. Right, and the next step is to find the derivative of all of that stuff. Right, so the derivative of the first one, it says we take the derivative of the inside. So that's negative sine of x divided by the inside. Right, we take the derivative of the inside and divide it by the inside. And here we take the derivative of the inside and we divide it by the actual inside. And we can simplify this a little bit, right? This is negative tangent, I believe, if sine is on top, plus 1 over 2 plus 2x minus 35x plus 1. That's a little bit simpler, I guess. But then we know that our actual derivative, the one that we care about, is the original function divided by 5x plus 1 to the 6th times the derivative of the natural log of the function. And so that's how we use logarithmic differentiation, right? We can combine it with any sort of function that we know how the derivative of it works. Any product, quotient, or raising to a power can be expanded using logarithms. And we get something like this. So next time, this is, I believe, our last big sort of rule or process. We might think we're mostly into applications from here on out, starting with related rates. So that's what we'll be talking about next time to round up the material for exam 2. So I'll see y'all then.